Assalamu alaikum. Today we will discuss the system steady state error performance. In this lecture, we will try to cover simplest way how to analyze the system steady state performance. So first of all, let's make a block diagram. So that we have a plant which has an output C of S for a given input R of S. It has a transfer function G of S. So writing it in a closed loop form, we can introduce a block, later we will discuss it, in series with the plant transfer function. Again, it will give us the output. We will feedback this output to the input set. So for the sake of illustration, we name it for time being. This is your plant transfer function and this is your controller transfer function. So we will define different type of controller here to illustrate about this topic. So let's assume that we have a transfer function for the controller. We call it G1. G1, which is at this moment I'm not taking it as a function of S. So in the later part we'll discuss it why we did that. So what happens is that considering G1 as a first case is equal to K. Now again here we have a function E of S, which is the error built using the output and the reference signal. You will get the error signal and we will provide this error signal to the controller function, and this will generate a controlled output U of S, and this will be provided to the plant. So assuming that we have selected G1 of S as just proportional gain. So what will happen now if we will get the E of S? So let's to make the things a bit simple, we will drop the function of S and we will use simple time domain analysis, that E of t is equal to R of t minus C of t. Assume that we are working in time series. So now here, considering for the illustration purpose, we assume that G of S at this instance it is equal to 1. So now here, by using this figure, we can see that if this function is equal to 1, then what will happen? C of S or C of t is nothing but it is equal to E of S multiplied with the G1. So now what will happen, that if we can write it in the time series, C of t is equal to E of t into K, because as we selected G1 of S in the form of K. So writing E of t with respect to C and system gain K, we can identify that as K will approach to infinity, we will get E of t will approach to 0. But there is a important parameter in this definition, that we have a output C of t, as we can see that by using this function. This is directly proportional to the magnitude of the error signal. So by using this factor here, if this will be equal to 0 as k will approach to infinity and e will approach to 0. So by virtue of these two conditions, especially this one, which summarizes the whole derivation, that we cannot have a zero steady state error is not possible if we have just a proportional controller cascaded with plot. So what is the remedy for this kind of behavior? So we will do a simple adjustment to our controller transfer function, is that we are going to select g1 of s equal to k by s. So, or make it a bit illustrative, we can write k into 1 by s. So this 1 by s factor, this one, is the integral factor that we want to incorporate into our existing system, this one. By virtue of this change, we will see that we are going to find a transfer function that will make the overall error equal to 0, but the output will not be equal to 0, which was the case that we observed in the earlier case. Now in this case, we got the 0 error, but here the plant output becomes also equal to 0, because 0 error was directly being fed to the plant transfer function and the controller input, and this affects the output of the whole transfer function. So again, writing the same equations that we did earlier, for the output signal, C of s was equal to E of s. For this, we are following this network, right, into your plant transfer function, or you can know in this way, we are just giving the name as a controller transfer function. So domain what will happen, that C of t can be written as, where this 1 by s factor is replaced with the integration operator on the error signal. So by using the by parts integration, C of t is equal to k times, let's call it 0 to some time t1 E of t dt plus t1 to infinity E of t dt. Discuss the reasoning behind using this by parts integration. So let's draw a curve. This is a time series curve. So assuming that as we are increasing the gain of the controller, this will make, as we discussed in the previous topic, that this will affect the error performance, and it will decrease the error till this time, and at this time it is assumed that it becomes 0. So this is a graph for E of t, and this is magnitude of E of t. Absolute values, right? So what we did here is that we divided this whole domain into two parts. One is the one factor incorporates the time interval 0 to t1 such that in this time interval we are getting a non-zero error. Let's say we define this at E of t is not equal to 0, and in this time interval E of t is equal to 0. So let's a bit graphics here. So we have divided this whole picture into two parts, right? So this part, this we are drawing the diagonal lines, error is non-zero, right? And in this vertical bars, your error is equal to 0. So now we can see that even the error is equal to 0 at this time interval, after this time interval, what happens? We have a non-zero value of the error before this time interval. So we have used the by parts integration to validate this explanation mathematically. So what happens that, let's use that we have some constant value, let's call it C1, which is the consequence of this non-zero error signal, plus, okay, this is whole multiplied with the plus k times 0, because this whole factor will be equal to 0. So this factor will, you can just eliminate this thing. So what we will get? We will get a constant output k times C1 for a output response EFT. So what we have concluded at this instance, that here we got the error equal to 0, EFT equal to 0 as time approaches to some maximum value. So but C of t is not equal to 0, which is our ultimate task, because the controller effort will be useless if you are not going to get any output signal. So we should have some output signals so that we could get our desired response at the output. But if our controller is working in a way that it is making the output error equal to 0, yes, that is the desired point, but it is also making the system output equal to 0, then this is a useless activity. To cater this problem, what we did, we have incorporated an integral action into the system. This integral action helps us to minimize the error signal, but making a non-zero response, or you can say the non-zero output signal. So this helps us to gain both the parameters. One is the system steady state performance improvement, and the other one is the non-zero output signal. So hopefully this lecture would have give you insight into the actual scenario that we are able to sketch using this whole mathematics, is that whenever we are required to minimize the steady state performance, steady state error of the signal, we need to incorporate integral action. In the future lectures, we will see that we are going to use the PI controller, proportional plus integral controller, to minimize the steady state error and improve the steady state performance of the system. Okay, till our next lecture, hopefully you will understand further these concepts. And in case of any questions, you can comment on the comment section box. Take care of yourself.